All right, I am going to skip mean value theorem because it is pretty self-explanatory. And if you check the answer key, it's essentially the whole idea of the mean value theorem is that IROC equals AROC, right? So that f prime of x equals f prime of c at x equals c. Let's go straight to optimization with absolute mins and maxes. That first one, a very similar problem, was explained in the very first video. So remember, same thing that we did in that video 1. You would find the derivative and find the zeros of said derivative. Because it asks for absolute min and max, you also have to check those endpoints. And then from there, you're identifying the highest and lowest values from that table that you create, including endpoints and where f prime of x equals 0. So if you need more of that, go to that first video. It's the first problem on the first video. That being said, I'm going to skip straight to these optimization problems because I feel like those require like the most explanation of the remaining content. A rancher has 500 feet of fencing to build a corral for livestock against the side of a barn, which will not need any fencing. So here's my barn. Find the dimensions of the corral that will maximize the largest area. So here's my fence right here, right? And make that kind of nice. And I know that like inside that fence we have some animals. This just makes me happy to do. Here's another one. Okay, whatever. There's animals in there. So we are looking for what area is maximized. So our primary equation, the equation that we're looking to maximize, is area. And that area is going to be that x times y, or that length times width. We're going to have a secondary equation, and secondary equation in this case is more than likely going to be perimeter since I'm told that I have 500 feet of fencing. So perimeter, here's my secondary, and the secondary equation is equation that sometimes is given. Usually you come up with it, and its main purpose is to get everything in terms of one variable. So that perimeter in this case is just 2x plus y because we have 2 widths and 1 length. And that entire perimeter is going to be 500. I'm going to solve this for y so everything can be in terms of x. And I get a equals x times 500 minus 2x. When I simplify, this is 500x minus 2x squared. Now I know that for like maximization, this is where a prime equals 0. So I'm going to find that a prime. Also changes from positive to negative. So remember, it's important that you're always verifying that it's actually a maximum and not giving you a false maximum. So we're going to take a 2x out, and we are going to be left with 250 minus x. After I do that, I get 2 solutions. We have, oh my goodness, I just solved. I did not derivate at all. Let's derivate first. When I derivate, a prime is 500 minus 4x. There we go. And then I'm going to factor out. So I'm going to pull that x out and get 124 out and get 125 minus x. So I get that x equals 125. Let's check just to make sure. This is a positive linear y-intercept with a negative slope. So positive y-intercept, negative slope, it's linear. So that 125, we'd be coming down. So from positive to negative, yes, that is a maximum. Dimensions then, we know it's going to be 125 for my x value. So for my y, I'm just going to take it and plug it into that equation. 500 minus 2 times 125, 500 minus 250. So I get 250 for y and 125 for x. That is going to match letter A. Last optimization. A poster is to have an area of 180 square inches with 1-inch margins at the top and bottom sides of a 2-inch margin at the top. All right, so here's our poster. The area of the poster is X times Y. And we want the dimensions of the largest printed area. So this is what our primary, we're going to have, our area is going to be our secondary and primary equation. I also know that we have some strange margins going on, right? So here would be my X and here would be my Y. We have 1 inch margins at the bottom and the sides. So 1 inch. 1 inch margins on the sides. So this right here is 1 inch. This right here is 1 inch. And then we also have a 2-inch margin on top. So our area right here, our primary area, is going to be not only X times Y. We are not just maximizing that. We are trying to maximize this inner part. And the dimensions for this inner part are going to be a little bit different because my outer dimensions are X and Y, which means my inner dimensions, this inner length is going to be this original length minus 3. And this inner width is going to be my outside width minus 2 because we're getting rid of those margins. So what we are trying to maximize is X minus 2 times Y minus 3. And that is my primary equation that I'm looking to maximize. The area in general is 180. So I'm going to set 180 equal, solve for Y, and get Y equals 180 over X. Once again, the whole point of your secondary equation is to substitute into the primary to get it down to one variable. So I have A equals X minus 2 times, I'm going to sub in 180 over X minus 3. And then I'm going to distribute. So I have 180, X over X cancels, minus 3X minus 360 over X plus 6. Combine like terms, so I get negative 3X minus 360 over X plus 186. Because I'm maximizing, I'm finding that derivative. So that's negative 3, oh boy, x to the negative 1. So that's going to be plus 360 over x squared. And remember what I did here is in my brain I was like, okay, this is negative 360 x to the negative 1. So that becomes positive 360 x to the negative 2. So that's where that came from. And then that constant cancels. Because I'm maximizing, setting it equal to 0, so we get 3 equals 360 over x squared. I'm a huge fan of cross multiplying, so we're going to do that now. 3x squared equals 360. And then take that square root. So x is going to be, we're going to negate the negative. Normally we would say plus or minus, but because we're optimizing, a negative value is not going to give us optimal. So we're just going to use the positive square root of 120. If I simplify that, you can leave it at positive square root of 120, or you could say, what is that? 2 square roots of 30. Both of these answers work. We're still looking for dimensions though, so we also need that y value. So you could say your x is root 120, your y is 180 over root 120. And these are both in inches. We can leave it there. If you chose to simplify and give simplified answers, like what a multiple choice would probably do, your x would be 2 root 30 inches. And your y would be, you'd have 180, so we'd have 90 over root 30, and then we'd rationalize to get 3 root 30 inches. So there are my two dimensions right here. Remember, don't worry about simplifying if it is short answer, but if it is multiple choice, they will more than likely have the simplified form.